Good morning, students. Chapter 3, Current Electricity. Yes, second lecture. Today we will discuss about electric current density. Electric current density. Yes, in NCERT textbook it is not given in detail, but yes, you have to study this for JEE and NEET purpose. Okay, see what is electric current density. Here it is. It is one conductor. See, it is one conductor. In this conductor, I am taking this cross-sectional area. This cross-sectional area is A, and we know that area vector is always perpendicular outside. So area vector is in this direction. Current flowing, it is also in this direction. It is also in this direction. Okay. Then, if a current I is uniformly distributed over area A, over this area, current I is uniformly distributed, then what is current density? What is current density for this conductor from this cross-sectional area? Current density is defined as J is equal to I upon A. Current density J is equal to current I upon area A. J is equal to I upon A. Clear? Okay. See here, note one point. I and A, they are in same direction. I and A, they are in same direction. Clear about this? So whenever area vector is in direction of current, current density J is equal to I upon A. Simple. J is equal to I upon A. Clear? Okay. SI unit, I upon A, so it is ampere per meter square. So yes, first case is easy, in which A and I, they are in same direction. Now see second figure. See here, second figure. In second figure again, one conductor. Yes, I have changed cross-sectional area. It is cross-section. So area vector is always perpendicular outside, so it is area vector. Okay, and current I is going in this direction. So here in this case, area vector and current, they are not in same direction. Or in second language, we can say, see, here current is perpendicular to cross-sectional area. Current is perpendicular to cross-sectional area. Here current is not perpendicular to cross-sectional area. So let us consider a cross-sectional area A which is not perpendicular to current. So in this case, you have to take component of cross-section area in direction of current. See, for example, if this cross-section area A makes angle theta with I, then what is component of A in this direction? It is A cos theta. It is A cos theta. Then what is current density at this point from this cross-section? Current density in this case, J is equal to I upon A cos theta. J is equal to I upon A cos theta. So see what is difference between case 1 and case 2. If I and A, they are in same direction, then simple, J is equal to I upon A. But if they are not in same direction, then you have to consider component of area vector in direction of electric current. Okay, so J is equal to I upon A cos theta. If I make I as subject, then J A cos theta. J, electric current density, is vector quantity. And its direction is in direction of current. If current is in this direction, then yes, it is direction of current density. Okay, so I is equal to J A cos theta. A area vector, just vector quantity. J vector quantity. So I can write this J A cos theta as J dot A. So I is equal to, it is J dot A. Clear about this? Now see from this equation, I is equal to J A cos theta. What is theta? Angle between J and A. If they are in same direction, current and area, they are in same direction. What is angle between them? 0. Cos 0 to 1. Then I is equal to J A. You will get this equation. Clear about this? Okay. So it is difference between two cases. Now if from this entire cross-sectional area, current is not uniformly distributed. Then what you have to do? First of all, you have to take elements Take one very small element of cross-sectional area, find what is current flowing from it. Then take another cross-sectional area, find what is current flowing from it. Take another cross-sectional area, element, find current flowing from it, and to find total current, I is equal to this integration J dot dA. It is integration J dot dA. So you have to remember this equation. I is equal to integration J dot dA. Now, the direction of current density is same as the direction of current because current density is vector quantity. Okay, so remember what is equation of J? J is equal to current upon area. Current upon area. Clear about this? Now see, we have one question. You are given this figure. Okay, yes, you can easily understand this figure. Current I is equal to 2 ampere. This angle is 60 degree. It is cross-sectional area given. Its value is A is equal to 1 centimeter square. You have to find current density J. You have to find current density J. Now see, from figure it is clear. Current is not perpendicular to cross-sectional area. Current is not perpendicular to cross-sectional area. Okay, so which equation you have to use? Yes, J is equal to Y upon A cos theta. Okay, now see here, carefully. Here, area vector. Area vector is always perpendicular. If it is cross-sectional area, then area vector is in this direction. It is area vector. Clear about this? If this angle is 60 degree, okay, area vector is always perpendicular, then this angle will become 30 degree. This angle will become 30 degree. Then what is angle between I and A? I and A is 30. What is angle between I and A? 30. What is angle between I and A? It is 30. Clear about this? Clear about this? Most of students write angle 60 degree. But hello, this 60 degree is angle of this plane with current. Of this plane with current. We have to find angle between I and A. Between I and A. And what is angle between I and A? It is 30 degree. So now if you want to find current density J, then J is equal to it is I upon A cos 30. I upon A cos 30. Clear about this? Because see, I and A, they are not in same direction. So if you take component of A in direction of I, then yes, you will get it is A cos 30. Clear about this? It is A cos 30. Clear about this? Okay, so put value of I, convert in meter square, put value of A, okay, cos 30, okay, solve this question and write down your answer in comment box. Okay students, next topic, Ohm's law. What is Ohm's law? See, yes, you do not have to perform any experiment. We will perform some experiments in practical lab. But if you take a small cell, okay, of 6 volt, 12 volt, etc. Okay, you connect two wires and if you touch the wire, yes, you will experience a shock, but very minor shock. Yes or no? Yes. But if you touch any 230 volt or 240 volt, that is in our house, okay, then yes, you will experience a shock. Yes. Again, if you touch cable of overhead train, yes or no, then yes, you can observe from such results that current flowing from object depends on voltage, that is potential difference. That is potential difference. After numbers of experiments, scientist Ohm suggested or he gave one relation between electric current flowing from conductor and potential difference applied between its two ends. Potential difference applied between its two ends. Okay. Yes, current flowing from conductor depends on potential difference between two conductors, between two ends of conductors. That we will also prove in practical lab. Okay. Now what is statement of Ohm's law? See, under definite physical condition, that is at constant temperature, if current I is flowing from a conductor and V with the potential difference between ends of conductor, then Ohm's law states that V is proportional to I. That we have already studied in 10th. Okay, V is proportional to I. Current depends on potential difference between two ends of conductor. If we remove proportionality, we have to add some constant. So V is equal to Ri. V is equal to Ri. Or I can also write V upon I is equal to R. V upon I is equal to R. Clear about this? What is this R? R is constant of proportionality and it is called resistance of conductor. It is called resistance of conductor. Okay, so now you have to remember this equation. R is equal to V upon I. V is equal to IR. V is equal to IR, where R is called resistance of conductor. Its SI unit is ohm. Yes, you know it. And it's denoted by the symbol ohm. And it's denoted by the symbol ohm. It's another unit we can say from this C. R is equal to V upon I, means volt per ampere. It is volt per ampere. Clear? So yes, it's another unit. It's another unit. Okay. Now, this resistance of conductor depends on first temperature. Resistance of conductor depends on temperature, material, and dimensions of conductor. You have to remember these 3 points. Okay. Resistance of given conductor depends on temperature. If we vary temperature, then resistance also changes. Resistance also changes. That's why in Ohm's law we have to take this finite physical condition, that is a constant temperature. Because if temperature is constant, resistance remains constant. And if resistance remains constant, then V is proportional to I. Then V is proportional to I. So first point you have to remember, resistance depends on temperature. Yes, in this chapter, in next topics we will study dependence of resistance on temperature. Okay, yes, we will see one theory. Resistance depends on material. Resistance depends on material. Yes, you know this resistance depends on material for metals, for non-metals, for semiconductors, etc., etc. That we will study. Okay, next one is dimensions of conductor. Resistance depends on dimension of conductor. Dimension means its length, its cross-sectional area. And yes, in next lecture we will prove this. Okay, how? Resistance depends on dimensions of conductor. We will prove this thing. Okay, so right now you have to remember these 3 points on which resistance depends. Okay, now one extra point. The reciprocal of resistance, that is 1 upon R, is called conductance. Reciprocal of resistance is called conductance of material. Its unit is mho and its symbol is just mho. Clear? Okay, completely reciprocal. Definition is also reciprocal, unit and symbol reciprocal. Clear about this? Okay. Next is C. Yes, Ohm's law. It is not fundamental law. Why it is not fundamental law? Gravitational law. We can apply anywhere, in any condition. It does not depend on temperature or another external factors. Okay. Coulomb's law. Yes, we can apply anywhere. But this Ohm's law is under definite physical condition. For example, if temperature is constant, then resistance is constant, and then V is proportional to I. Okay, so under some conditions we have to apply this law. That's why it is not fundamental law. Okay, now most important thing, IV graph. IV graph. It is called characteristics. It is called characteristics graph. Okay, so if you are asked, okay, what is characteristic graph of Ohm's law, then you have to draw this graph. Okay, see what is this graph actually? It is variation of current with voltage. It is variation of current with voltage. We will perform one experiment in lab. Okay, we will take one conductor, voltmeter, ammeter, and one battery. Okay. We will change value of voltage. Then yes, we will get different values of current. We will change value of voltage. We will get different value of current. You have to make one table of voltage V and current I. Clear? From table, you have to draw graph. And yes, when you will draw graph, it will be a straight line. It will be a straight line. Clear about this? Okay, so remember, IV graph for a conductor obeying Ohm's law at a constant temperature will be a straight line, and such relation is called linear relation. Clear about this? Clear about this? So here IV graph is a straight line. It means device obeys Ohm's law, and the devices which obey Ohm's law, they are called ohmic devices. So if I ask you one MCQ, okay, for ohmic devices IV graph is, then yes, your answer is a straight line. A straight line. For Ohm's law, for ohmic devices, IV graph is a straight line. Yes, a straight line. So yes, it's a slope. Yes, slope will give some value. Here what is slope? See, slope, I am taking these 2 points. Okay, so slope means this theta is equal to delta I upon delta V. Slope is equal to delta I upon delta V. Delta I upon delta means 1 upon R. So remember this MCQ again. Second question. Slope of I versus V graph gives. Slope of I versus V graph gives question mark. Okay, comment answer. Okay, in comment box. Clear about this? Okay, so it is Ohm's law. Okay, now in next lecture we will study about this dimensions of conductor. How resistance depends on dimensions of conductor. Clear? Okay students, now we will see dependence of resistance on dimensions of conductor. Okay, see case 1. We have one conductor having cross-sectional area A and its length is L. Clear about this? So, for this slab, dimensions are cross-sectional area and length. Cross-sectional area and length. These are called dimensions. Okay, so let current flowing from this conductor perpendicular to cross-sectional area is I. Potential difference between two ends is V. Okay, then yes, what is resistance of this conductor? R is equal to, it is V upon I. So now, if I have any another identical conductor, having same cross-sectional area, having same length, having same current, having same voltage, then yes, its resistance is also same. Clear about this? Now what is second case? See, here it is. Placing two slabs side by side. Such two slabs having same cross-sectional area and same length, they are placed side by side like this. Means we can say it is a series connection. Which connection? It is series connection. Okay, so see here for this slab, okay, cross-sectional area is same for both. Yes or no? Yes. What is now length of this conductor? What is now length of this conductor? It is 2L. Means here, see what is condition. We have two dimensions, A and L. First case, remain area A same. Okay, area A remains same. And length is double. And length is double. Clear about this? From two dimension, change only one dimension and another dimension remains same. For example, here area is same and length is doubled. Length is doubled. Then what happens? See, yes, these two slabs are in series connection. So, just we will study in this chapter. Okay, whenever two conductors are in series connection, current flowing from them is same. Current flowing from them is same. Clear about this? Okay. Between two ends of one conductor, potential difference is V. Yes, there it is. Okay, so between these two ends, potential difference is V. Also, between two ends, potential difference is V. So, between two ends of composite slab, what is potential difference? It is 2V. Clear about this? So, here I have one conductor in which cross-sectional area is same but length is doubled. Okay, so in case new resistance R dash is equal to 2V upon I. 2V upon I. is equal to V upon I. What is V upon I? V upon I is R. So it is 2R. So what happens? See now, length is doubled and this resistance is also doubled. So doubling length doubles resistance. So what is the relation between resistance and length? R is proportional to L. R is directly proportional to L. If I increase length, resistance increases. If I decrease length, resistance decreases. Clear about this? Okay. Doubling length doubles resistance. Now next case. See. Cutting it lengthwise means see. Out of 2. Cross-sectional area and length. Here area is same and length is doubled. Now here we will change area and length will be same and length will be same. See, length is same. I am cutting this slab in 2 parts. Okay, in 2 parts. Cutting it lengthwise. See, this total area is A. This total area is A. If I cut this area into equal parts, so what is this upper area? It is A by 2. See here it is. This area is, it is A by 2. This area is also A by 2. Clear about this? Clear about this? Okay, so if I am cutting this conductor slabwise, if I am cutting this conductor slabwise and I am taking only one part, okay, like this, then what happens? See, cross-sectional area becomes half, length remains same. Now I is current flowing from cross-sectional area A. So what is current flowing from cross-sectional area A by 2? Yes, it is I by 2. So current from each slab is I by 2. Potential difference for each slab is V. Potential difference for each slab in parallel connection. It is nothing but parallel connection. In parallel connection, potential difference remains same. So for each slab, potential difference is V. So now what is new resistance? New resistance RS is equal to voltage between 2 ends divided by current flowing. Voltage divided by current flowing. So it is 2V upon I is equal to 2R. Is equal to 2R. Hello, here area is halved, but resistance is doubled. So what is relation between them? See, halving cross-sectional area doubles resistance. It means cross-sectional area and resistance, they are inversely proportional to each other. So I can write R is proportional to 1 upon A. Resistance is proportional to 1 upon A or inversely proportional to A. Clear about this? So if you combine these two conditions, R is proportional to L and R is proportional to 1 upon A, then you will get R is proportional to L upon A. Okay, if you remove proportionality, you have to add some constant. So R is equal to rho L upon A, where rho is called resistivity of material. Rho is called resistivity. Rho is called resistivity of material. And yes, this resistivity depends on temperature and material, but it does not depend on dimension. See, that is difference between resistance and resistivity. Resistance depends on temperature, material and dimensions. Resistivity depends on temperature and material only. It does not depend on dimensions. Clear about this? So yes, resistance depends on dimensions of conductor. And what equation you have to remember? This R is equal to rho L upon A. Rho, that is resistivity, L, length of conductor, A, cross-sectional area of conductor. Clear about this? Pause your video and write down for